Start. So, good afternoon, participants, and welcome back to 12th lecture uh, for the course on high pressure physics. So, we will start from the last lecture where we have left. So, in this lecture, or in this hour, I will try to cover the pressure scale calibration in the higher pressure region, then diamond anvil Raman gauge in multi-megabar region, and I will try to give you updates on these. And the various, I will try to summarize the techniques and tools for achieving pressures in the megabar region. And then why we want to pursue this kind of pressures, why we want to go for these kind of pressures. And then I will start high pressure and high temperature. So here I will try to give the flavor of, like, if we include another thermodynamic variable temperature with pressure simultaneously, what kind of science and what kind of techniques we required. And I will try to give some examples for that. So let us start with the pressure scale calibration. So pressure scale calibration at megabar pressures. So the question is how to measure the pressure accurately and adequately. It is very important to measure pressure inside your sample chamber. And I assume that some things has been already told to you guys by Dr. Himanshu Poswal. Like there are two kinds of scales, primary scale and secondary scale. And in the primary scale, the basic definition is like, here we use the basic definition of pressure. That is, pressure is nothing but force per unit area. So you measure the force applied on a specified area. So you measure the area as well as force. And by doing that, you can directly calculate the pressure. And in the secondary scale, we calibrate this scale with the primary scales. And here we use different kind of calibrant materials, which have some physical properties which changes pressure prominently. Why prominently? Because you want to have more accurate measurement of pressure. So this scale is calibrated with respect to the primary scale and with known equation of state of standard metals. So in the primary scale, as I said, there are other methods, like if you can measure the bulk modulus with some other methods such as ultrasonic measurement. So in ultrasonic measurements, these are the measurements where you can independently measure the bulk modulus of a material. And if you can measure the volume by X-ray diffraction, so simultaneously by measuring the bulk modulus and volume by XRD, you can use this equation. Like we know that B0 or bulk modulus is negative of logarithmic derivative of pressure with respect to logarithmic volume, or you can consider it minus V0 dP by dV at isothermal conditions. So if you integrate this thing, it comes out to be P at pressure at some volume minus pressure at volume 0. Here volume 0 is at room temperature. So that is nothing but integral of B0 over volume. So by integrating this, you can actually find out the pressure at any volume. So as in the secondary scale, the most famous or most prominently used scale is ruby fluorescence based pressure measurement, where we know that ruby is nothing but chromium doped alumina. We all know alumina Al2O3. So if you dope this Al2O3 with the Cr3 plus, here is a transition metal with 0.5%, then it gives fluorescence. We also call this alpha phase of Al2O3 as corundum. This alumina source, like if alumina is alumina crystallizes in the R3 bar C rhombohedral crystal structure, and you can see the crystal structure of this alumina and this octahedral arrangement of aluminium and surrounding oxygen. So along the C axis and in A axis. So you see that when you substitute Cr3 plus, so Cr3 plus goes into the alumina lattice in place of aluminium, and the Cr chromium has slightly larger size than aluminium. So what it does, that it gives some kind of strain into the lattice. So chromium forms an octahedral with the surrounding oxygen ions, and splitting of energy levels occurs due to this octahedral crystal field and spin orbit interaction. So we have, with this chromium and oxygen, we have octahedral environment as well as spin orbit coupling. So it gives rise to this kind of energy level diagram. So what happens, like when you pump these 3D electrons of chromium 3 plus by using some suitable laser excitation like 532 nanometer or 633 nanometer, then these 3D electrons, they go into the 4T2 electronic levels, and after some time they fall into 2E state, and this E state is, which was degenerate, it splits due to this crystal field is splitting, and when these electrons, they go to the ground state like 4A2. So from these two states of 2E, they go to ground state 4A2, and we get two lines corresponding to these two transitions. One is called R1 and another is called R2. R1 is at higher wavelength and R2 comes at the lower wavelength. Like you can see here, the energy gap between the upper one and the ground one is higher, so its frequency is more. So the energy difference between these two levels is exactly 1.4 nanometer, 1.39, which is the difference between R1 and R2 lines. So here, this is a typical Ruby pattern shifting with pressure. Like if you apply pressure, like at 1 atmosphere, these are the R1 and R2 lines. R1 is stronger than the R2. So we generally measure the pressure with respect to the R1 line. And these R1 and R2, both these lines shifts with pressure. So this shift with pressure can be calibrated against the known equation of state of metals. And that's how the Ruby scale is more frequently used in the high pressure experiments, especially the static high pressure experiments used with the diamond anvil cells. So in the next slides, I will tell you like typical experimental setup, which is used for Ruby fluorescence based pressure measurement. So this is an optical diagram which shows like you require an excitation laser, and you focus this excitation laser on your sample, and then the fluorescent lines and the Ruby fluorescence lines, they are collected through this objective lens and through a collection lens, and of course you use the pinhole and through collection lens to a spectrometer, and then you can record these Ruby fluorescence lines and get the pressure by using the calibration parameters, which I will be showing in the next. So here, in the earlier years, like even in 1973, Barnett and Pirmani, they calibrated this scale up to 19.5 kilobar with the known Decker equation of state of sodium chloride. And here is the scale calibration. If you see, this y-axis shows the pressure in kilobar, and this x-axis shows the Ruby R1 wavelength shift. So this is shift here in nanometer, and on the above scale, the Ruby, like on top horizontal top scale, it is frequency shift delta nu in centimeter inverse. So what they determine up to 20 GPa, like 195 kilobar or 20 GPa, that pressure shifts very linearly with the Ruby fluorescence wavelength. So they plotted this and gave a parametric linear relation, like delta lambda by delta P is nothing but 0.365 nanometer per GPa. So this is a linear pressure dependence up to 20 GPa. But if you go to higher and higher pressures, the pressure dependence is no more linear. So for more higher pressures, the pressure was calibrated again by Mao and Bell. Later on, Mao and Bell revised this Ruby pressure scale and calibrated the Ruby pressure scale against the equation of state of several metals, several noble metals, especially gold, silver, copper, aluminum, and quasi-hydrostatic and platinum and non-hydrostatic conditions. And they also included both kind of conditions like hydrostatic, quasi-hydrostatic, and non-hydrostatic conditions, and extended it up to quite high pressures like 800 kilobar at 80 ZPa kind of pressures. So by fitting this data again, the Ruby fluorescence line delta lambda in nanometer and versus pressure against the data. So what they found that pressure in GPa can be A by B and in bracket delta lambda by lambda 0 power B minus 1, where delta lambda is change in wavelength. So it is wavelength shift. And pressure, so they fitted this data and they determined the value, parameter value A as 1904 and B as 7.665 for quasi-hydrostatic conditions. So if you know the delta lambda and lambda 0, so lambda 0 is your excitation wavelength. So like laser wavelength, the laser which you are using to excite the Ruby fluorescence. Like it could be either in the visible range like 532 nanometer or 531 nanometer or red laser also. And they also determine like if you include the non-hydrostatic conditions, if you are going for the non-hydrostatic conditions, then you have to substitute B equal to 5, then you will get the accurate pressure. So these are very, very like frequent used pressure scales up to 80 gigapascals. But beyond that pressures, like what happens, like beyond that pressures, Ruby itself, the signal becomes very weak as well as broadened, Ruby broadened. Another thing also, like Ruby scale itself, like the two lines R1 and R2. So if you see these two lines, R1 and R2, there is a constant difference between these R1 and R2. And this difference is a signature of hydrostaticity of your sample, or the medium surrounding your sample, whether the transmitting medium is hydrostatic or not. Actually, you can determine by measuring the difference between R1 and it should remain constant, and it is a measure of the hydrostatic environment. So if your sample fills truly hydrostatic environment, then the difference between R1 and R2 line, or separation, R1 and R2 line separation remains constant with respect to pressure. But if it changes, that again a signature that your pressure transmitting medium has become non-hydrostatic, or your sample is feeling non-hydrostatic environment. So like here is a cartoon or picture showing hydrostaticity of the different pressure transmitting mediums. Like if you see isopropanol is only hydrostatic up to just 40 kilobar or around 4 GPa. Beyond that, you see the drastic change in pressure broadening of the Ruby R1 line. Even the Ruby line broadening, like FWHM, full width half maxima of Ruby lines, they are also very good signature of hydrostaticity. Like this pentane, isopentane is hydrostatic up to like 7 GPa or 70 kilobar around. Methanol is hydrostatic up to 8 GPa. And 4:1 methanol ethanol mixture is hydrostatic up to 9.5 GPa. So 9.5 GPa, this is quasi-hydrostatic, and almost quasi-hydrostatic up to 20 GPa. And one also uses methanol ethanol water mixture in the ratio of 16:3:1, which is hydrostatic up to 15 GPa. So these are kind of like different mixtures of alcohols, pentane, isopentanes, and ethanol, methanol water. They are very easily usable hydrostatic medium, and very like poor man's hydrostatic medium. ideally, inert gaseous media or inert gases, they are very good pressure transfer medium, which I hope that Himanshu might have spoken to you guys. Like if you use helium or argon or neon, like helium is truly hydrostatic beyond 20 GPa, and even quasi-hydrostatic up to 60 GPa pressures. And argon, although it has its like freezing pressure is lower, but even then, because these are the inert gases and they are softer solids, so softer means their shear stress is very less, and that's why this inert gaseous media are very good pressure transfer medium than this methanol, phenol, or other alcohol water mixtures may be. But only thing is that like if you want to use the inert media or inert gas media, you have to necessarily use the gas loading apparatus. So gas loading can be done either by the cryo at low temperatures, like cryo by using the cryo loading method, or by the pressurized gas you load inside the gas loader. So like as I said, Ruby pressure scale has some limitations. Like you can't use Ruby pressure scales in megabar region or in multi-megabar regions. So the limitation is the signal itself, the Ruby fluorescence signal that diminishes in very high pressures. And other thing is that like at megabar pressures and beyond that, your diamond itself, like on the other day I told that diamond itself, it becomes, it shows cupping kind of behavior or lensing effect, because of which your Ruby signal also get very diminished. So that is the limitation of Ruby pressure scale, that it is not applicable beyond 1 megabar pressure, or you can say there will be very large errors in the pressure values if you still want to use the Ruby scale. And another point is that like as higher and higher you go in the pressures, your sample chamber area becomes smaller and smaller. So there you don't want any extra things, like you don't want to put Ruby chip or any other thing which will be detrimental for your sample or experiment. So what happens, like due to non-hydrostatic stresses and due to weakened and broadened fluorescence signals, Ruby pressure scale is no more usable in the megabar region. So in that case, the people have suggested, like first time in the 1985, Michael Hanfland and Carl Sassin, they suggested about this diamond anvil Raman, like Raman scattering signal from the diamond anvil as a measure of pressure. And in fact, even in 1985, they showed that it also has this diamond anvil Raman, like first order Raman peak of diamond anvil, it has linear dependence with pressure up to 30 GPa. So basically what they gave the concept that you can use the elastic response of the culet phase. Like diamond culet phase has the elastic response with respect to the normal stress which you are applying. So using that elastic response of the culet phase of the diamond anvil to the normal stress, one can really measure the pressure by measuring the higher side Raman A's of the first order Raman peak of the diamond anvil. So to develop an optical method to determine the pressure in multi-megabar region, the first order Raman peak of diamond can be used. And this first order Raman peak at normal pressure is around 1333 plus minus 1 centimeter inverse. That is very strong first order Raman peak of diamond. So here in this pressure scale, what we use the high frequency edge of the first order Raman band. I will show you what do you mean by high frequency edge in the next few slides. And then this is coincident with the Raman shift of the culet of the anvil due to normal stress. Remember, this is not what in some scales or in some pressure scales, people also put inside diamond cell a small diamond chip and measure the Raman out of that diamond. So that is not. This is the response of your culet itself. And using this method, like elastic response of the culet phase, this calibration was performed up to 310 GPa, 310 gigapascal, using equation of state of platinum sample inside DAC by Akahama and Kawamura. And they published a famous paper on pressure calibration of diamond and Raman gauge to 310 GPa. So up to this 300 GPa, people use his calibration scale of Raman shift. And the advantage in this scale is you are using the diamond itself. So you are not using any other thing which you have to put inside your sample chamber. So here is the, like what I said, that second higher order is. So this is a typical Raman spectra, first order Raman spectra of diamond anvil. So this is that 1333 centimeter inverse peak which I say you, and it comes like this. So here he has shown up is only from 223 GPa up to 286 GPa. And if you see at the ambient condition, this peak is very sharp peak. And you don't get these higher order edges. So as you increase the pressure, this shows the higher edge at the higher order. So by determining this edge, so what you do to calculate this position accurately, you take this first order derivative, and the value in this around this point shows you the exact position. So like at higher pressure of 286 GPa, this point is around 1801 centimeter inverse. So you see at ambient condition, the Raman peak comes at around 1333 centimeter inverse, and at 286 GPa, this comes around 1801 centimeter inverse. So there is a huge difference of around 470 centimeter inverse going from ambient conditions to 1800 centimeter inverse. So this is basically, this shows the elastic response of the culet of your diamond anvil. So this is the calibration graph which Akahama and Kawamura, they have fitted with the pressure versus delta nu by nu zero. So here they have plotted delta nu by nu zero. Nu zero is the first order Raman peak, like 1330 centimeter inverse, and delta nu is the change in the position of edge with respect to the nu zero. So this they have normalized with respect to nu zero, delta nu difference with respect to nu zero, and plotted with respect to pressure. So they have fitted this, and this has fitted with a nice equation like P in GPa is K0 delta nu by nu zero 1 plus 1 by 2 K0 dash minus 1 into delta nu by nu zero. So you see here that K0 comes out to be 547 GPa. And K0 dash is 3.75. So your culet response, it behaves like a platinum ball with a bulk modulus of 547 GPa, and derivative is as 3.75. So this scale he has calibrated up to 310 GPa. So most of the experimentalists who go beyond megabar, they use this scale to calibrate their pressure or to determine their pressure in their experiments. So like here, I am showing these numbers, like in the new, this is a calibration curve with respect to pressure and the frequency of the higher side A. So you see the plot. Like they again, these guys like Akahama and Kawamura, they initially in 2004, they have calibrated only up to 240 GPa, but in I think in 2009, they calibrated it up to 310 GPa, and they have also plotted various other scales, like scales of Vohra and other people who have calibrated. So you can see here what kind of QLED they have used. Like in different experiments, like in one experiment, he has used the sample as scandium and another aluminium, and scale which they have used to calibrate with respect to is platinum. So like with 35 micron QLED, they have reached like 223 GPa, and even with 35 micron, they reached up to 297 GPa to calibrate. So they have done the XRD experiment with platinum and sample as scandium, and in other cases aluminium. And of course, simultaneously, they also measure the pressure using the diamond anvil by Raman spectroscopy. So, and if you want to go really in the 300 GPa range, you have to use the QLED diameter of 30 micron. You see how small this QLED will be. So what they have fitted in this, the best fit is like this equation. So by this equation, and by knowing the value of K0 as 547 GPa and K0 dash as 3.75, you can really determine the pressure if you can measure the Raman lines in the higher pressure range. So in the next, I think in 2010, they again calibrated this pressure scale up to further higher pressure. Like they calibrated this pressure scale of diamond anvil Raman gauge up to 410 GPa. Why I am saying gauge? Because this is a kind of scale which really helpful in measuring a smaller, like starting from like even 20 of GPa up to very high pressure like 400 GPa. So they calibrated this scale up to 410 GPa. So you see here, this comes from the table of the diamond, this peak, that the first order Raman peak. And the higher age peak that comes at the 408 GPa at 1907 centimeter inward. So you see the age here. So just by measuring this point, or if you want to know accurately, you take the first derivative of this thing and you get the deep. So the deepest point here, that gives you the position of this age. So they calibrated like, and they plotted all their previous data and with the present data. So whatever calibration they have done earlier, it was something like this, like up to 310 GPa, this was going like this. But when they measured up to 410 GPa, there is a deviation, slight deviation above this 300 GPa, and they tried to fit it again with the present data, all the initial pressure values, including the 410 GPa range, and they have given this kind of fit for this pressure values as 3141 minus. So they have fitted it quadratically with respect to the Raman age frequency. So this, but this pressure scale is what they have fitted in 2010. Its validity range is only beyond 200 GPa, because to fit this higher side data, they have taken the data only beyond the 200 GPa, because below 200 GPa, this scale does not fit. So you see that, like going this kind of pressures, they have used very, very smaller size QLEDs, like they have used 15 micron QLEDs, 20 micron QLEDs, 30 micron QLEDs. Ultimately, they reached 400 GPa with this 20 micron QLED. So you can imagine how difficult or how it is to work with this 20 micron QLED. Not only like starting from alignment and then alignment of the cell anvil and then gasket preparation, sample loading, doing experiment. So to achieve this kind of pressure, and then to characterize those samples which you synthesize or which you make at this kind of pressures, you really need very, very bright sources and very like good Raman systems which have very good spatial resolutions, very fine spatial resolution. So this is work from Akahama and Kawamura in 2010, where they have calibrated this scale up to 410 GPa. And quite recently, see this diamond Raman is, it has been like people have tried to calibrate it even up to 0.5 terapascals. Like nowadays, people are trying to achieve terapascal region of range of pressures using the diamond annual cell, as I showed in the last few lectures. Like people use different kind of diamond annual cells, like double stage diamond annual cells, toroid diamond annual cells, and they can really achieve pressures beyond 0.5 terapascals. So in this pressure range now, the diamond Raman has been tried to be calibrated, and this is at Raman spectra of diamond A's at 477 GPa. So you see the sharp Raman line from the table, and then the response, elastic response of the QLED. So you see the A's here. So this is 20 centimeter inverse around, which corresponds to 477 GPa. And this is the diffraction pattern of gold inside the diamond annual cell fitted, and its lattice parameter comes out to be 3.361. So Admets et al., they have given a universal diamond age Raman scale up to 0.5 terapascal, and they have tried to elaborate the implication of this scale for metallization of hydrogen, which if time permits, I will show in the last of my lectures about hydrides and hydrogen. So what they have done really, like here you see, they have taken all data till now from Akahama and other runs and from other people, and they have tried to fit starting from very low pressure up to almost 500 GPa. So what they show that if you take the Akahama's calibration, like beyond 200 GPa one calibration, it comes like this. So this feed does not feed the data from the Admets, this calibration data. You see all the colors things that Admets, they have tried to get it. So what they did, they used all the earlier data and they tried to fit it, and they have given a universal pressure scale in the form of P equal to A into delta omega by omega 0, where omega 0 is again the first order peak of Raman, first order diamond Raman peak. And in their case, they have taken omega 0 as 1332 plus 1332.5 centimeter inverse. And they have tried to fit this, and delta omega is the, of course, difference from the age difference, second age difference from the first order Raman peak. So they have fitted a quadratic equation in the delta omega by omega 0 and determined the parameters values, like A parameter as 517 and B as 764. So what they say that you can really determine accurate pressure from almost ambient conditions up to 477 GPa using this pressure scale. So in that sense, they are saying that actually diamond annual Raman can work as a universal pressure scale for all kind of experiments. The advantage here is that if you have a sufficiently good Raman system, you can use the Raman scale to measure the pressure, because necessarily if you are using the diamond annual cell, you have the diamond QLEDs on for your pressure determination. So what they were saying that earlier scale, whatever that was determined by the Akahama and Kawamura, that pressure scale is overestimating the pressure values beyond 400 VPa. So what they say, you see here, like if I take the 1900 centimeter inverse line, a horizontal line, so it cuts the universal scale at slightly before than the scale from the Akahama and Kawamura. So that means Akahama and Kawamura pressure scale was overestimating the pressure than what has been determined by Hermits et al. So that's why they claim this pressure scale to be a very accurate and universal kind of pressure scale. So this is the story with the pressure determination and pressure scale calibration. So now to summarize with, like, what are the techniques and tools for achieving megabar pressures? So in in practice or practically speaking, you require very tight tolerance between mechanical piston and cylinder parts of DAC. Like this we call as the cylinder and this part we call as the piston. So these are the two mechanical parts of this diamond anvil cell, which you see here as assembled. So this cylinder and this piston, they fit into each other. So there is a tolerance between this inner diameter of the cylinder and this outer diameter of this piston body. So if this outer diameter of this, outer diameter of this extruded piston body and inner diameter of this cylinder is higher, like if tolerance is higher, then this is kind of loose fit. You can very easily fit one into each other. But at the very higher pressures, what happens? They start wobbling. So ideally, to go very high pressure, if you want to achieve really good pressure, you need to have very good machining of these two parts. So you need the very tight tolerances in terms of engineering drawings, like the clearance between this inner diameter and this outer diameter of protruded portion of the piston. So this should be of the order of 2 to 5 micron, not more than 5 micron actually. And you see here, not only that, there are many other features which one needs to take care if you really want to achieve higher and higher pressures. So like this is a symmetric type of diamond anvil cell which has a conical opening, and this conical opening can also be used for different purposes like for laser heating and other things. So here you see this assembled cell, and we have this screw for applying the pressure, for applying the force, and there are these washers which we are using in a particular combination with the applying screws, and you see the scale here. This is just 5 centimeter of diameter of the outer OD of this symmetric diamond anvil cell. 5 centimeter is 50 millimeter, which you can very easily hold in your hand, hold in your palm. So such a gentle device, using this and proper culettes and proper backing plates, like these are the small things, they are actually diamond seats. We also call them backing plates. Generally, in some cases, they are made of hardened steel, or here, when you want to achieve high pressures, they are made up of tungsten carbide. Tungsten carbide are very hard materials. So with this specialized seeds, and again, the manufacturing or fabrication of these seeds also matters a lot. Like this should be perfectly parallel or plane. If they are not plane, if they have more roughness, these seeds, then your diamond actually, if you stick the diamond to these seeds, there is a chance that something like epoxy or something goes inside you, in between your diamond and seed, that may cause the failure of experiments. So actually, there are many things which one needs to take care, not only the diamond cell and diamond, when you want to achieve higher pressures, like the gaskets, gasket thickness, gasket material, diamond anvil, of course, and what kind of experiment are you planning, whether you are planning experiments up to 20 GPa, up to 40 GPa, up to 100 GPa, and again, what kind of characterizing technique you want to use, like you want to go it for XRD, you want to go it for optical measurements like Raman, IR, or you want to do the transport measurements like resistivity measurements or magnetic moment measurement, what kind of measurement you want to use and up to what pressure and with what kind of attachment, all these things covers the choice of different parameters, different experimental parameters. Like typical backing plates and diamond seeds, backing plates are like diamond seeds, those are used to mount the diamond anvil on top of that. And the typical thickness of this tungsten carbide backing plates is 5.3 mm, and with the 1.1 mm opening and at the back end. And that gives, sorry for this, I think, typographical mistake. You have this accessible angle range from 50 to 65, not 650, from 50 to 65 degree angle length. But if you want to really go very high pressure, this accessible range again becomes very lower and lower. That is, again, I think Himanshu might have told you the principle of massive support. So you want to keep more massive support. So you want to minimize this angular opening. So these backing plates also, this diamond sheet should be polished enough. And then opening of backing plates, there's a trade-off between massive support and this opening angle. So to achieve very high pressures or megabar pressures or beyond megabar pressures, you really require beveled diamond anvils with culate sizes 100 micron and less, like depending on what kind of pressures you want to go. And of course, this is a one kind of one-way journey. So once you achieve higher and higher pressures, your diamonds they crack on mostly on release. Many a times, you may also lose your diamond anvils while aligning the cells or while loading or while pressurizing the sample. Many a times, there are many, like the success rate is really very less in this kind of experiments. These two diamonds, like the diamond which we are using for diamond anvil, they need to be mounted on the backing plates very precisely. So each and every work of high pressure, starting from choosing proper anvils, choosing proper diamonds, mounting them, aligning them, everything, like if you want to go to higher pressure, becomes very, very meticulous. One has to ensure that the center of the culate matches with the center of the backing plate while mounting these diamonds on its top. Otherwise, you will not get proper signal. Even alignment of DAC for megabar experiments also requires very special attention. So many of the times, you may crack the diamond while even aligning. Like diamond, we know that they are the hardest material. So even if you touch one diamond with other diamond, they may go. So due to the very small sizes, actually to alignment and doing all these things, you have to do everything under the stereo microscopes with larger optical zoom. And in some cases, you may really require monocular microscopes also with larger optical zooms. Unlike normal DACs, you cannot take the risk of touching the smaller cured diamonds on top of each other, as that may lead to cracks in the diamond. And because this is a purely experimental science, so unless you do all these things with your hand, you will not realize, I think, what I am saying. So alignment of DAC in principle, it is very easy. Like you have to do just translation and rotation of the diamond to make these culettes on top of each other, looking at the Newton's fringes between two diamonds. So you have to, like, if you want to align the translation, you have to look the edges of the diamond culet. If you want to align the tilt between these diamonds, you have to just give the rotation to your one of the anvils, which has the arrangement of rotation. So in some cases, only translation is required, where you have very perfectly polished diamond and perfectly polished seeds and perfectly polished your mechanical assembly of cylinder and piston. So even the gasket materials are also very, very important. The metal seed which you want to use as your sample chamber. So to achieve very high pressure, one uses metallic gasket of rhenium and tungsten of appropriate thickness. Why I am saying appropriate thickness? Again, depending on the type of experiment and typical pressures you want to achieve, the thickness of this gasket varies. Out of these, rhenium is more favored because rhenium has high yield strength at higher pressures. Tungsten is little brittle. So rhenium is more often than used than tungsten. So like once you make the gasket, once you indent your gasket, you necessarily use like either electrode discharge machines to drill the gasket, metallic gasket, and these are the typical optical high zoom stereo microscopes which we use for this kind of work. And more often than not, if you want to use really very smaller gaskets, you want to go for very high pressures, then you need to necessarily use this laser drilling systems where you keep rotating your gasket and the pulse nanosecond laser, nanosecond pulsed IR laser falls on this gasket and it starts cutting your gasket and it makes a nice hole. Like suppose your culet diameter is 100 micron, but I am saying here, so this is the indented portion of 100 micron, and then you have to drill a hole of 40 micron out of that. So generally, 1/3 of culet we use for sample chamber. So this is kind of achieving megabar pressures. So like once you have achieved, once I have taught you or lectured that you can achieve megabar pressures by doing this thing. So the question is, why do you want to achieve megabar pressure? Why do you want to do this kind of experiments? So the answer is like this kind of experiments, they really can generate very novel phenomena which you are not able to see at ambient conditions or even at the lower pressures. Like if you see here, like this is a very common material, water, which is which is one of the largest used of the air on the earth, and this is a very ubiquitous water material. So you see the phase diagram with pressure and temperature of water so rich. Like if you increase the temperature, it goes into the vapor and the gaseous phase. If you increase the pressure, it goes into the solid phase. So even in the solid phase, like if you increase the pressure, you know that it can become ice. Like generally we think that just by decreasing the temperature, water becomes ice. It's not only that, by increasing the pressure, even at the room temperature, you can make it ice. And ice can have different kind of phases, like almost more than 30 phases ice has with pressure and temperature. And of course, this is a phase diagram of first element of our periodic table with only one electron and one proton. Nothing can be simpler than hydrogen in our whole world, right? So it has only one electron in the first orbit and one proton in its nucleus. So purely quantum mechanical system. and its phase diagram is still far from understanding. Like it is still evolving phase diagram, and it is very elusive to get metallic hydrogen, and people are still pursuing. So megabar pressures can always throw many surprises and many novel phenomena. So that's why people want to go this kind of pressures, or it is worthwhile to experiment at this kind of pressures. So what, in a nutshell, what I say is that it spans the phase space area into a different regime and shows the path for different physical phenomena. Not only that, actually the compression energy, if you see, if you are pressurizing, so the C or compression energy P delta V term, which goes in the order of several tens of electron volt, once you achieve these kind of pressures, which is very suitable for electronic changes in the material. And with these kind of pressures, there is really a competition with the chemical bond energy. Like this hydrogen molecule, so they have typical bond energy in the order of electron volt. So there is a competition with the compression energy and the chemical bond energy, and especially in simple molecules of low Z elements such as diamond, water, hydrogen, nitrogen, there are many phenomena can happen. Like you can really break these molecules and they can form something else. They can form some extended solids or something like that with very peculiar properties. So these materials may show completely different phases and new phenomena. For example, hydrogen is expected to metallize at higher and higher pressures, but metallic hydrogen is still elusive, as I told you in the last slide. So still, many more experiments are required to understand hydrogen at multi-megabar pressures. So this megabar business, it always throws many surprises. So things are not like common in this. So like I want to show this another example of elemental solid like sodium. We all know that sodium belongs to the first column, and sodium is an alkali metal with the neon as its core and valence electron in the 3s1. So there was a report, or there was a like paper by Ashcroft on the constitution of sodium at higher densities. So what he said, that if you go to higher densities, sodium would show semi-metallic like electronic properties. And in fact, in sodium, in the megabar pressure range, negative melting curve has been observed. What is the melting curve? So basically, the temperature pressure behavior, like when you melt, it's like melting temperature in general of solids with pressure, if you increase the pressure, the melting temperature in general increases. But in case of sodium, if you go to higher pressures, it reverses, like it has a negative slope. Like it reaches a maxima in the temperature pressure phase diagram and it goes down. And of course, after phase transition to the BCC phase and FCC phase, it shows different behavior. So this melting of dense sodium was a landmark paper in the megabar pressure range. And that's what I was saying, that if you go to the megabar pressure range, it always show like surprises. So should we close it? Maybe not. So in the next slides, actually, I will delve into, like till now, what I was showing about only the pressure. So if you want to study really the materials, the way they are inside the earth, you need to involve the temperature also. So you have to have high pressure and high temperature. And not only that, like with temperature, you can really go to the PT phase space. So maybe in the next lecture, I will tell you more about this high pressure, high temperature, about the technique and about the other things, and how do you measure the temperature at this pressure, and then what kind of research or what kind of results are obtained out of these studies. So in the next lecture, I will tell you details starting from here about the high pressure and high temperature. Yeah, thank you. So if any questions are there, I can.
Ajay, after you attend to the questions,
Yes.
I may like to have a brief chat with you.
Okay. Okay, you can. Yeah, I'm saying video audio not available on YouTube.